Hey, good afternoon, everybody. We're getting on 12 o'clock here. Wanted to thank everybody for attending the next installment here of the Retwo webinars. Today, we're going to be proceeding with a presentation on geohazard identification and mitigation. This is Jeremy Berger speaking. I apologize, I don't have video feed here this morning, so hopefully everybody can hear me clearly. I'll be kind of the MC and fielding some questions here at the end of the presentation. Chris Brixius, if you could advance slides for me, please, to the next in line. Wanted to start out with some housekeeping here. Traditionally at Retwo, and to help bolster our safety and quality procedures here internally, we start out with a safety and quality moment. First and foremost, pertaining to safety. My neck of the woods in Northeast Pennsylvania, we've been seeing quite a bit of rainfall lately. That's teamed up with driving considerations. I know many of us have not been driving like we used to based on the COVID impacts, but making sure you've got good tread on your tires. In addition to ponding water on the road, make sure you're paying attention because hydroplaning is a big issue right now. Moving on to a quality moment, again, pertaining somewhat to COVID, and my apologies for continuing to bring that up, but electronic communications, we're doing a lot by email these days. We get a lot of the same names in the systems, Bob's, Brian's, Jeanette's, etc., making sure that you're CCing the right people, double checking your email addresses while you're proceeding forward and sending those out. At the onset of this and the RSVPs that went out, we are offering a single PDH credit for attending today. Through the RSVP process, if you were interested in that, you should have responded to Jenna Swihart, who fielded that request. We'll get you a certification out confirming the PDH offering. If you have not done that and you are in interest of receiving that credit, please let me know or send again directly to Jenna Swihart, who can be referenced in that RSVP, that request, and we'll make sure that we get you squared up at the end of this. Lastly, questions. Since we are in a Microsoft Teams live webinar, we're not able to hear you, but you're able to hear us. And such with questions, there is an icon at the bottom of your screen in the toolbar that says provide Q&A or show Q&A. We'd ask that you please type in or key in your questions to us, and we are going to save those till the end. We got about a 45-minute presentation here with about 10 to 15 minutes at the end to field those Q&As. And we'll make sure that's squared up. With that, Chris, if you'd advance, please. I'd like to give a small introduction on some of our presenters today. We'll start from left to right. Dave Mosteller. Dave's got about 23, 24 years of experience in groundwater development, analysis, permitting, and natural gas consulting in various plays for us here at Retwo. Longstanding figure, and Dave helps out on a daily basis with some liaison efforts to regulatory agencies and supporting our overall midstream and exploration and production efforts. Next, in the middle, Ms. Felicia Bechtel. Felicia has over 30 years of experience in surface, marine, and borehole geophysical consulting. Her environmental and engineering expertise have applied to the work here with Retwo in respect to energy, local, state, federal, commercial, and industrial markets as well. And last but not least, Mr. Brixius. Chris has over 20 years of experience in geotechnical engineering and environmental consulting, and he works through the process of many different geohazard analyses and restoration and reclamation processes with us on a daily basis, as well as some additional support on sinkhole investigation. I would like to note that with this presentation, folks, although there's many geophysical hazards throughout the United States, we're going to focus quite a bit on Pennsylvania, Ohio, and West Virginia, and more specifically to a couple specific geohazards that Dave Mosteller is going to outline further. With that, again, thank you for your attendance. I'm going to turn you over to our technical presenters. And Dave, I believe you're first up on the block.
Thanks, Jeremy. Good afternoon, everybody. Brix, we can move ahead to the next slide. So what are we going to talk about today? We're going to talk about geohazards, and geohazards are geological hazards that are the results of natural active geologic processes. These can be hazardous to people or infrastructure, or they might happen, out in a remote area with no hazardous impacts. To the right, there's a list, but we're really going to talk about the big three in the tri-state area: karst and sinkholes, landslides, and mining impacts. And I am going to throw a fourth one in there, and that's inadvertent returns related to directional drilling. We are seeing a lot of regulatory scrutiny over that, so we are going to talk about HDDs and IRs as well. Next slide, Chris. So why are we talking about this? Well, in typical fashion, we've got a lot of regulation that we've got to meet these days in relation to geologic hazards. Again, we're going to talk about Pennsylvania, Ohio, West Virginia, and some of the federal influences. A lot of this stuff comes out in Pennsylvania first, and other regulatory agencies tend to follow. So we are going to talk a lot about what we're seeing in Pennsylvania. And we're seeing that in the ESCGP3 permitting process with geohazard mitigation plans. We've got the Pennsylvania Department of Environmental Protection's trenchless technology guidance. Ferc has similar guidance. They call it HDD guidance, but it's very similar to the PA regs. Licensed oversight and the importance of geophysical evaluations when we're looking at some of these geohazards. Next slide. So in the ESCGP3 permitting process, you start off with a notice of intent. Number 4 in that notice of intent is an evaluation of geologic or hazardous soil conditions. Slightly different language is used across this document in the Ferc doc, but it's essentially the same. And in this section of the NOI for the ESCGP, we're talking about expedited review. And if geohazards are present in your project area, it's going to be ineligible for expedited review. And it's really hard these days to get most projects through the expedited review process because of all the issues we have to address. Next slide, Bricks. Further on in the NOI for the ESCGP3, again, we talk about naturally occurring geologic formations or soil conditions, and DEP's asking you to evaluate those for your project area. If they are present, you need to include a geologic hazard mitigation plan with your NOI, and Bricks will talk a little bit more about that later. And they flat out say if you've got hazardous geologic conditions and you don't address them through the mitigation plan, just don't submit the NOI. So they're pretty blunt about that. Next slide, Bricks. Again, I said we were going to touch on the HDD and inadvertent return piece. We're seeing a lot of this come through with current projects. Pennsylvania DEP has put out their trenchless technology guidance, and they're defining trenchless technology as multiple crossing methods that don't involve trenching. So HDDs, guided bores, auger bores, things like that. This guidance came out of a settlement between DEP and Mariner 2 East projects. It set up a stakeholders group to both look at alternatives analysis and the technical guidance for HDDs themselves. Next slide, Bricks. So what are we seeing out of that document? Upfront permitting steps and assessment, heavy reliance on alternatives analysis, geologic and hydrogeologic evaluations, water supply identification and sampling, as well as geotech and geophysical work to kind of tie all that stuff in to the design of these. Felicia's going to talk more about the geophysical aspect of that, and Bricks the geotech, but a lot of emphasis on those items. Next slide, Bricks. Tying this in to the federal level, Ferc has HDD guidance that they put out last October. It's very similar to Pennsylvania. Language is a little different, but same kind of upfront requirements. Next up, Bricks. One of the big things we've seen come out of this new, it's not necessarily new regulation, but new focus on these items is the involvement of licensed professionals. And we're seeing this at the state and federal level. They want to see professional geologists, professional engineers, geotechnical engineers involved in the construction aspects of these projects. Again, both at the state and federal level, we've had projects that require professionals to be on site. We've even seen a case, it was a Ferc case, where they required a PG or a PE to be on site. The Ferc inspector came out. There was no licensed professional on site, and they shut the job down. So that's just something to keep in mind as we move forward from the permitting to the actual construction of these projects. Next up, I'm going to hand it off to Felicia Bechtel to talk about Karst Geohazards.
Thanks, Dave. Appreciate that. So I do want to talk about Karst Geohazards, and any of you on this webinar may or may not be familiar with Karst. It's named for the type locality of the Kras or Karso Plateau in Slovenia and Italy, which you see a picture on my screen. And it's a beautiful terrain. It is a geologic setting that occurs in areas with carbonate rocks, whether it's limestone, dolomite, sometimes gypsum, but in a wet climate. So for a karst terrain to develop, you need to have carbonate rocks and water. And you see from the setting, it has a characteristic topography. It's beautiful, low rolling hills, standing ponds. There might be little streams running through it. It looks very dimpled. And the reason it looks dimpled is because there's an amount of soil overburden beneath those green grasses, and then underlying carbonate rock that has been dissolved over time. And any of you on this webinar who are old enough to remember the Alka-Seltzer commercial of plop, plop, fizz, fizz, that's exactly what happens. Alka-Seltzer is calcium carbonate, and when you drop it in water, it fizzes away very quickly because it's designed commercially, but it fizzes away, leaving nothing behind. And that's what happens in a karst environment. Below the soil overburden, we have rock that's being dissolved by infiltrating water over thousands to millions of years. Chris, could you give me the next slide, please? So there is a cartoon here that shows beneath those rolling hills a cutaway of caves, flooded caves, dry caves, disappearing streams that have developed over time. You see the dimpled ground surface. That may be surface expressions of depressions or actual sinkholes where material has dropped away into these underlying caverns or dissolved areas. Kind of think of it like bubbles or tubes in Swiss cheese, or a cutaway of a sponge where over time you can get so much dissolution that you don't have just cracks in rocks that are slowly getting bigger. You can develop actual underground rivers. And this is the only situation when someone can truly realistically talk about underground rivers. They don't exist except in a karst type environment, and they can exist at all scales. Next slide, please. So I show here a map of karst in the eastern United States, which is displayed by the black in the map. And since we're concentrating on primarily Pennsylvania, West Virginia, and Ohio in this talk, you can see that relatively speaking, there's not a whole lot of karst running through this area compared to the Midwest or the South. However, if you look at the pop out to the right, you can see that karst, which is the beige bands following the Appalachian mountain chain, these beige bands, which represent karst, actually intersect areas that are populated. So as we develop our cities and towns, we have to understand how to work carefully and develop carefully in karst environments. Next slide, please. So the process of karstification is actually a selective and positive feedback one. I have a cartoon for the first three panels on the left. One is just natural fractures in the rock. Rock gets cracked up, broken over time. And those natural fractures are tiny little water pathways. And over time, water flows through those pathways, dissolving the rock. Remember the Alka-Seltzer analogy, dissolving the rock and making a little cavity. That little cavity can take on more water or more soil. So over time, as more water falls into that crack, dissolves more rock, the crack gets bigger, it can take on more water, and we have this positive feedback loop where we have more dissolution, wider fissures, and more through flow, eventually resulting in possibly an entire karst plumbing system. And this is a photograph from Kentucky, Karst Cave in Kentucky. Next slide, please. And these solution cavities pose several geohazards. One of them being Rockhead Pinnacles. So this is a picture here of the, in Pennsylvania, the Antaladi Dam was being built in 1926, and all of the soil burden was pulled away to develop this dam, leaving this very pinnacled rock surface. And the reason it's pinnacled is those deep fissures in between the rock pinnacles are the places where water got in and dissolved rock and made them bigger and bigger and bigger and bigger and bigger. And they're so big, if you, Bricks can point out a couple of people for scale. These guys, these fissures are big. So you don't have a nice, clean, don't always have a nice, clean bedrock surface below the soil, even if you're in flatlands. So it's the soil overburden can hide a lot. Next slide, please. This is a picture of a current day quarry in Pennsylvania where not all of the soil burden has been removed, but you can see the Rockhead Pinnacle tips sticking up. So I'm sure if the soil overburden were removed, it would look just like the picture that you see on the right from the Antaladi Dam. Next slide, please. So there are several geohazards that can develop as a result of karst, the first being subsidence, and these can occur in a number of ways, either by through the cracks in the rock, either by the soil overburden getting washed or flushed down through the cracks in the rock, or we can have caves developing from water infiltrating from a distance, caves developing under an area, and as the cave grows, the roof is actually growing towards or stoping upwards towards the ground surface, and eventually there's not enough support of the soil overburden below the stoping upwards cave, and the soil and rock collapse into this underground cave. So there are a number of ways where subsidence can occur in karst environments. Next slide, please. The second geohazard is groundwater contamination. In a karst environment, remember that water can travel fast over long distances very quickly. And this is very well illustrated in the case of Walkerton, Canada. In May of 2000, Walkerton, Canada has a small town of about 5,000 people. And in May of 2000, almost half the town population became seriously ill and several people died as a result of an application of sewage sludge outside the town, not barrier, but outside the town boundaries, where normal groundwater flow calculated that it would take at least 30 days for water infiltrating at this place where they were going to apply the sewage sludge. It would take at least 30 days for water to get to the town wells. They didn't realize they were on karst, so they applied the sewage sludge inappropriately, but not unwittingly, and the people became very sick. So when they, after the fact, went back and did dye trace studies of the area where, in wells in the area where they had applied the sludge, there was a 26-hour travel time from a nearby well to the town well, whereas the dashed line that you see on the figure, that should have been the 30-day travel time from normal groundwater estimation. And in a well inside the 30-day travel time groundwater estimation, the travel time between well 9 and the contaminated wells was 5 hours. So people got sick really fast, and it's simply because they didn't understand the karst plumbing system lying beneath them. Next slide, please. The third geohazard is in earth moving and support difficulties. You know, as we develop buildings, wells, all sorts of things, we're doing a lot of drilling into the ground. And if we are not doing that carefully or with enough understanding of the underlying karst environment, it can cause all sorts of problems. We can do estimates from boring logs, how deep we think rock is, and as we drive a cast pile, we might hit a floater, or piles might dogleg on pinnacles, or if we're drilling shafts, we might go from a rock pinnacle into a water-filled void, into a rock pinnacle, into a clay-filled void, and we have very little understanding of that, except that you know to expect that when you're in a karst environment. Next slide, please. We also have the same problem if we're doing a horizontal directional drilling, which is the yellow line that appeared. All of these, as we do horizontal directional drills, we may hit all of these encounters. And similarly, next slide, please. If we're doing horizontal directional drilling, next slide, we may get inadvertent returns. So we're doing HDDs with drilling mud, we're installing HDDs with drilling mud, but if the HDD crosses these fissures, the mud can make it to the ground surface and appear as an inadvertent return. Next slide, please. So in karst environments, there's a lot of uncertainty using conventional exploration, drilling wells, looking at rock cores. Here are two representative rock cores taken from a karst environment, and with the soil overburden being in red and the limestone rock and in purple, and potential voids or fissures in black. And if we were to put these, place these two borings side by side, whether they're 10 feet apart or 100 feet apart or 1,000 feet apart, we as scientists and engineers like to make interpolation and inferences between, or interpolation between hard pieces of data. So we might draw lines and say, okay, well, this bed looks like this bed, and that's probably what's going on. But if you look at, next slide, please. If you look at a coring in between those, we can see that we're, in some cases, dramatically incorrect. So conventional exploration does have a component of uncertainty in karst. Next slide, please. One of the things that we can do and should always do at the start of a project is desktop reviews. They're fast, they're cost effective, and they range from geologic mapping and reports that are published, karst feature databases, well log databases, historical aerial photographs, Lidar, fracture trace analysis. I'm not going to go into any discussion of these because Chris Brixius is going to talk about this at a later time in the talk, but please know that they're out there and they should always be done at the start of a project. It can save you a whole lot of heartache in later stages of a project. Next slide, please. Another technique that we can do, and this is my area of specialty, is geophysics, which is simply non-intrusive subsurface imaging. I try to relate it for people who aren't familiar with it as the earth science equivalent of medical radiology. We don't get the crystal clear picture, but we do get a sense of a fuzzy picture. We use a variety of techniques to look for targets underground that may be sensitive to the energy that we use in those techniques, so we can look for things like bedrock pinnacles or air or water or clay-filled voids underground. Next slide, please. So there are 6 common karst conditions, and they really fall into 3 categories: a solution cavity below the top of rock, which is the left vertical panel, a solution cavity with infiltration, which is the center panel. So we've got water, we've got a solution cavity below the top of rock, and then we've got water somehow making its way into that solution cavity and carrying material with it. And the last on the right is the solution cavity with dropout. We may not have water, but there's again a potential conduit to cavity under both the rock, and material can drop into it and cause eventual collapse. Next. So these 6 common karst conditions, and depending on whether there's no rock relief, so there's a flat-lying bedrock surface with solution cavities underneath, or bedrock relief where we have the pinnacles that we described, and places where water can the underlying bedrock preferentially. There are a variety of geophysical techniques that we can use to look for these types of conditions. We can use microgravity to look for voids below the top of rock. We can use spontaneous potential or electromagnetics or electrical techniques to look for places where water is infiltrating. So look for the water pathways that could lead to these. And we can use seismic and sometimes ground penetrating radar to look for areas drop. They may not have water moving, but they have disappearing into underlying features. Next slide, please. So there's no geophysics for. I've listed here the general 6 that we use, the nuances and in terms and decreasing terms of applicability and cost. So we have microgravity, electrical and electromagnetic, seismic, spontaneous potential, ground and desktop review. You can see that microgravity is applicable to 6 out of 6 of those conditions that we described of dropout, infiltration, or just cavities below the top of rock. But it's also the highest cost. So you want to use gravity judiciously. You don't want to use it over a 20-acre area necessarily. You want to do other reconnaissance techniques and then hone in using gravity in the real areas of interest, load-bearing areas or building footprints or retention pond footprints, things like that. Electrical and electromagnetic and seismic can detect 5 out of 6 and 3 out of 6, and they're intermediate costs, but they cover a wider area, more reconnaissance level area, much more so than gravity. Spontaneous potential, looking for water pathways, 2 out of 6. Cost is pretty low. Ground penetrating radar, maybe 1 or 2 out of 6. It's a low cost, but it's also very limited by site conditions. Sometimes we can only see 2 or 3 feet below the ground surface with ground penetrating. Doesn't tell you anything that's going on any deep in that, depending on the site conditions. Desktop review is the lowest cost of everything, but it's applicable to 6 out of 6. So you really should always be starting with a desktop review and then figure out your game plan. So I am now going to pass it back to Dave. Thanks very much.
Perfect timing. My neighbor decided to mow his lawn. I guess this is our new normal, so bear with me if you can hear the zero turn flying around in the background. Next slide. Oh, sorry, Bricks, you're there. So I'm going to talk a little bit about hydrogeologic considerations related to HDDs, but this stuff really applies to many of the geohazards we're talking about, particularly the upfront work. Next slide, Bricks. So when we do a hydrogeologic evaluation, we do these for a lot of different types of projects, but the basics are the same. We're going to look at the geology and soils. We're going to look at the hydrogeology. We're going to look at water supplies and sample those before construction occurs. We're going to do fracture trace analysis. Felicia talked about different types of geophysical evaluations we can do. Bricks will talk more about the geotech side of things. But really, we're doing all these things up front to develop a story, and that story is a conceptual hydrogeologic model that's going to help us later on when it comes time to design our projects. Next slide, Bricks. So one of the big ones with respect to HDDs are identifying water supplies near your bore path. DEP and Ferc guidance calls for a 450-foot buffer. That bumps out to 1,000 feet in karst environments for a lot of the reasons that Felicia just talked about. We need to identify public water supplies within half a mile and any surface water intakes within a mile downstream of a crossing. We do rely heavily on the Pennsylvania groundwater information system when we're doing work, obviously, in Pennsylvania. It's not perfect, but it is a resource that we use pretty heavily when identifying water supplies. Big thing to note, construction-related impacts to water supplies are violations of permits and can result in fines. Next slide, Bricks. So once we've identified water supplies within our project area, we're going to notify those landowners and let them know what we're doing and that we'd like to sample their supplies. We'll go out, purge that well or water source until we get stable field parameters, collect our samples, send them to a lab following a recommended parameter list, and we get the lab results back. We'll prepare a sampling and analysis report and give that to the landowner for their records. Next slide, Bricks. So where it can get interesting is water supply complaints that pop up during active construction. You know, those must be reported. We'll typically set up a site visit, interview the landowner, talk about their well construction, talk about any history of water quality issues, whether that's a well's gone dry in the past, things like that. And we will collect samples again and send them to the lab for analysis. This time around, we'll typically include Xrd analysis for clay minerals, which in some cases can identify the potential for bentonite from drilling fluid. We'll compare those results with our pre-construction samples. And this is really a prime example of why we do pre-construction sampling. It gives us a baseline to compare to if there is a complaint later on. And I would say 9 times out of 10, when we go out on a water supply complaint, it's going to come back to be not related to construction. It's going to be a pre-existing aquifer or well construction issue. And those things are often pretty easy to decipher when we do these well complaint reports. Next slide, Bricks. So, you know, we've done all this upfront desktop field work, geotech, geophysics. What are we doing with that data? Well, we're using it to help design an HDD. You know, we want to steepen entry and exit angles so we can get into the competent bedrock faster. Often we'll lengthen a profile to allow us to get some more depth to potentially avoid features that we've identified. We're going to rely heavily on data monitoring to look at things like fluid circulation and any losses of circulation. Next slide, Bricks. So again, you know, active construction considerations. We talked earlier about having licensed professionals on site. Again, we're seeing that as a permitting requirement, as well as pretty heavy daily monitoring and reporting, some of which has to go back to DEP daily. We've developed inadvertent return response and reporting plans. Again, we talked about how we investigate water supply complaints. And then another big one are subsidence evaluations, where we've got subsidence features or sinkholes that might pop up during a construction project that have to be addressed. Next slide, Bricks. So on the monitoring front, there's a lot of people out on the right of way, you know, PGs, environmental inspectors, utility inspectors, other technicians. They're on foot, they're in boats, we're using drones to cover large areas. So one of the things we're using that upfront data is to identify potential areas where we might have an issue. If we see something along an HDD path where there's some heavily fractured rock, or we're going through a heavily karstified area, you know, we might put some additional people out on the ground to keep an eye out for IRs as we pass through troublesome areas. And with that, I'm going to pass it on to Bricks to talk more about the landslide and mining impact side of this.
All right. So, as Felicia and Dave have kind of touched on, there are requirements for a lot of midstream and upstream projects, especially in Pennsylvania, for a geohazard mitigation report. We have also titled these naturally occurring geologic assessment reports to sort of match the language in the permits. That report itself will cover a desktop evaluation of any available geologic resource that is out there, but also include a field reconnaissance that will kind of highlight any of the things that we find during our desktop research and then any observations in the field. Typically, what then follows as the next steps moving forward to mitigate any geohazard is an action plan, typically consisting of 3 steps. First will be an investigation, through test borings, test pits, geophysical survey to kind of quantify what the subsurface parameters are with regards to soil, rock depth, soil type, soil shear strength, and those factors. That will be usually followed by the engineered design of any mitigation. For a landslide, that would be a mitigation of that hazard itself to repair the slide. And then the final step is then construction. We're gonna be preparing construction plans for most projects with details and notes, but then we're gonna want to be in the field to guide that landslide repair, for example, with a qualified inspector that's going to monitor how things are occurring and make sure that they adhere to our plans. So let's back up to the first step. As far as a desktop evaluation, we're going to be using GIS mapping to overlay various maps and to help us out with the quantification of materials and types of things we're seeing. Here we have 4 maps over the same alignment of a project. The upper left is our geologic map that shows the geologic strata in this location. The upper right one is a soil survey map over the same alignment. Soil surveys are very helpful for quantifying soil origin, soil type, soil limitations, which could include shallow rock, seasonal high water table, those sorts of things. The lower left is slope mapping brought into GIS using Lidar data, which is readily available in all of our states. We can use that to do a color-coded map for slope steepness. On this profile here, the darker blue is the steepest of the slopes. And in this particular case, we kind of designed this pipeline alignment to avoid any steep slopes. And the lower right, we have that same alignment over the existing landslide hazard identification maps prepared by the USGS that are available for our region. Those maps are helpful for, kind of getting a feel for if there are existing known landslides or areas that are susceptible to landslides. So when you include all of these maps together, you kind of get a very good idea of what you're looking at as far as geohazards on a site. And then one of the next steps is to look at any mine maps if you're in Western PA or even in the anthracite coal region and West Virginia and Ohio. Every state has a platform that has all the scanned maps. The Pennsylvania Mine Map Atlas is very good and up to date. The West Virginia has a good mine database where you can see where the coal beds are, and in addition to any longwall mining or room and pillar mining. And then the ODNR Mines of Ohio map viewer is also another resource. So we're going to use these resources also for projects, and we're going to look for what available maps there are with regards to mining. The old maps from the early 1900s are in these resources, but also there's newer maps filed permits for longwall mining that are going to happen in the future. So that's very helpful to see those things where they underlie your project. The most common thing with surface mining, we might want to take a look at where we're expected to see coal seams. Some of the lithologic maps that are out there kind of show where you have the more thinner coal seams where they might outcrop at the surface. So when we're designing any project, we're going to want to prevent any acid mine drainage or arsenic issues by managing any of the surface or subsurface water on a project with relation to where you might expect any of these coal seam issues. Also out west, you have a lot of coal spoil piles, in certain areas. So if you have an alignment that's running through a known coal spoil pile, we're probably going to want to take some tests of that material to see, what the pH is and what is the risk to not only the pipeline, but also if there's water moving through that project, is it going to be a problem with acid mine drainage? If you're going to be excavating through a known seam, or you find something when you're excavating, or you expect it, you might want to be permitting the removal of that coal for economic considerations. But a lot of times you don't really have stuff that's very economic to remove, and we will be putting on our plans maybe a detail as depicted on the screen here, which is a storage pit where we're making an allowance for encapsulating coal spoils on site using a compacted clay or geotextile as a barrier. So I'm going to finish the talk, finish the rest of this talking about landslides. Here is a map of the United States. That large red area on the left, or on the eastern area of the Appalachian Plateau, is basically a large area where landslides are highly susceptible. So you see it's the largest area in the country. There's basically three main reasons here. The underlying geology is flat-lying beds of claystone, shale, and siltstone, which weather to very fine-grained soils, which interact with the steep slopes that are in this region due to that same geology. But also you have heavy precipitation. You have winter snows and snow melt, along with a lot of spring and summer thunderstorms that roll through this region. So when you have all of that water intersecting with steep slopes and fine-grained material, you have a recipe for landslides, as opposed to, say, the Pacific Northwest, where, you have rain, you have steep slopes, but you don't always have the same fine-grained clay soils that are widespread as they are in our region. In fact, this is not a new thing. Monongahela, one of the three rivers in Pittsburgh, is derived from an American Indian word that is translated as river with the sliding banks. So even the Indians knew what they were encountering in this region. Why is identifying these landslides important? Well, you have assets at risk all over the place. Here's a landslide on an embankment fill on a well pad. At the top of that slope, you have storage tanks, you have a drill up there, you have utilities, you have a roadway. If not addressed, this stuff will just keep happening. It'll keep moving, and then you'll have very high cost to repair anything that is impacted by further instability. Here's a good photo of what we're looking at on the micro level with regards to a landslide. This is a slip plane. From this photo, you can see that these are very wet clay soils. But if you look at that striation on that surface there, that is where the soils up top are moving against the soils at the bottom. When we're evaluating a landslide for the first time, we're going to be kind of looking for these features, and if we dig a test pit, we're also going to be looking for where this is located, because this helps us during the design process of how do we want to fix this problem. So we're going to want to design through where these slip planes are encountered. At a known slide, we're going to begin with an initial field evaluation. This is our most experienced geologist, Mark Maley, in Pennsylvania and West Virginia. He's fixed hundreds, if not, he's fixed hundreds of landslides. When we go out into the field, we have developed a landslide evaluation form that collects a ton of information on soil types, what we're looking at, measurements of the of the landslide, both height, width, depth. What are there any assets that are at risk as far as an existing pipeline, existing buried water lines, any other buildings? This is basically going to be our baseline form that we're going to be using for the future. If we're doing a lot of landslide evaluations, we have like a little, numerical rating system. So if we have 100 slides we're looking at, we're going to kind of rate them in order. So the client will want to repair the ones that are worst rated first. Moving along here, it's important to know that once you get to a landslide, you got to you're going to want to kind of address it with some sort of speed to it. You know, the photo on the left is late October. You can tell by the leaves on the trees, orange and reds. This is the slide that that is kind of creeping up to the top of the crest of a well pad. But just a few weeks later, you know, the trees have dropped. This is probably early December. That slide has grown significantly over time, and a lot of material has slid down the hill past the silt socks that were there previously. So, you know, it doesn't take long for things to grow over time. So as far as the mitigation process after a first initial field evaluation, one of our next steps is to begin with an existing condition survey. And typically we like to get out there with a drone survey because it's, you know, very cost efficient to do so. You can take an existing photo and see how things stand at one point in time. You can prepare the plans based off this survey, and then, you know, we were going to prepare profiles along every 25 or 50 feet along that that project. So we're going to prepare cross sections, and either through test pit data or test boring data, we're kind of going to develop a subsurface profile and the strength of those materials, the parameters that go into the geotechnical design, including friction angle, cohesion, unit weights. We're going to assign values to all of the strata, and then we're going to kind of then develop the repair plan, which will include a typical toe bench and benching scheme going up the hill. The drawing on the upper middle there shows a 2-to-1 slope, and we are just backfilling that with drainage and compacted lifts. However, the drawing on the bottom right, that one is a little bit steeper, and we need a geogrid to meet our required factor of safety. This is what our typical toe bench and bonding bench detail looks like. There's on the bottom left there at the base of the slope, the toe key, we have rock in that one. And then you have a benching scheme going up the hillside to the crest of the slope, which remediates this landslide. Here's our typical detail in three dimensions. The key here is you can see where we have drainage moving through this slope and down to a common area at the base of the slope where the water will outlet out of there. All right, so the next, I'm going to show you examples here of what this looks like in construction. The photo on the left shows, that truck is dumping rock into where the toe key is for this project. And then the photo on the right shows them covering that up, and they're going to then start working up the hillside with the benching scheme, through this slide. Is very important. It's got to be founded on competent rock or very stiff, hard residual soils. We're going to want to excavate through all the colluvium that is there. We're going to want to put a toe key outlet and drains in the back end of not only the toe key but benches that are going up the hillside. The next photo on the left there shows that this is one of the benches moving up, but on the back end of that slope you have a bench drain with a site drain that's at the back of the slope, that with the intent of collecting all water that's kind of moving laterally through that area. And then photo on the right shows a typical compacting lifts as we're moving up the hillside with a sheep's foot roller. Our inspectors will density test these soils so that they meet the specifics of the design that we prepared. And you continue moving upwards, compacting the lifts, and then at the end of the day, you'll have a reconstructed embankment. To be honest, this one doesn't look very steep, but it also highlights that if you have a lot of water and fine-grained soils, it doesn't take a very steep slope to cause a landslide. Very difficult, pipeline alignments in West Virginia, southwestern PA are typically, down through some steep terrain. This landslide occurred on one of those areas next to a stream. Due to the steepness, we needed a geogrid design in there to assist with the stability of the slide. So, we're going to have to be in some very inaccessible areas sometimes to get this done. In addition, these photos show the geogrid being placed on the benches as they're going up the hill. In the back there, you'll see an existing pipeline that we're protecting around too. So we have to take all of that into consideration. You'll see on the back end of the slope, we're benching this one back into bedrock. And just moving up here, continuing with this construction, we're just moving up in lifts with soil, and then on the photo on the right, you'll see some drainage at the back end of that slope. So the key to all of this is putting in drainage, making sure that the benches are under compaction control, and if geogrid is needed, that is also in place. And finally, I don't want to close without mentioning that there are alternative mitigation designs, including soil nails or retaining walls. The photo on the bottom shows a MSE wall on a project that we designed. It looks like it's a valve station for oil and gas project. However, this whole hillside was a landslide that we prepared, so we had to design an MSE wall through, while repairing the slide as we built this project. In general, these alternates are usually a little more expensive than the standard benching and grading schemes that I showed on the photos there. So, economic considerations are always what we take into account with our designs and how we are providing recommendations for these repairs. That pretty much ends how that very quick and fast discussion on landslide repairs. There's obviously a lot more that can be said about it. So now we'll turn it over to Jeremy for some questions and answers.
Thanks, Chris. Chris, go ahead and mute for me if you don't mind, please.
Yep.
Thank you. All right, folks. Well, appreciate again the attendance here today. We've had quite a few questions come in so far. Again, noting that please IM them in, key them in on that toolbar at the bottom if you have any others outstanding. Couple of other things to note before we get into those questions. You'll see on the screen right now, again, technical expertise as we kind of kick this thing off with Dave, Felicia, and Chris Brixius's contact information up there. If you'd so choose, feel free to reach out to them directly should we not get to your question here today, or should something come up to the future that you have additional questions on. To the comment of PDH credit, Ms. Jenna Swihart's email is up there. You can get with her if you would like that certificate and didn't previously request one. And in addition to that, we were asked during the presentation if these slides would be available to provide to the folks that attended here today. Traditionally, the link that you initially received for attendance will be available for about 90 days. That will have the live meeting here that you could go back through and either listen to or reinterpret at that point. And as well, if you would like the actual PDF slides, please email Jenna Swihart, again, listed down there email-wise, and we'll make sure we get those out to you in hard copy also. With that, we'll go ahead and jump in here on some questions. Miss Felicia, I believe this one pertains to you directly, and the question was, do you have example cost or cost per area for microgravity evaluations?
That's a great question. Thanks, Jeremy. I have to have a couple qualifiers. One, we typically do microgravity on a grid. Either a 10 by 10 grid, measurements in a 10 by 10 grid, or a 10 by 15, sometimes a 10 by 5. And we determine what is the best grid to use depending on the size anomaly we might be looking for and the area we have to cover, because obviously there's a cost benefit analysis. The more data you collect, the higher resolution data you have, but the more costly it is. So we try to balance our clients' needs and budget in every single proposal that we do. That being said, we can do using a 10 by 10 grid, which would be considered a high resolution survey. We can do an acre in about 3 days of work. And a general rule of thumb for a gravity survey, production-wise, is about $4,000 to $5,000 a day, That's soup to nuts, not including mobilization, because we are called to work all over the country, but that includes all the equipment, all the field work, all the data processing, and all the report. So if you have an acre area and you want a high resolution survey, you're probably talking about, you know, $10,000 to $15,000. I'm sorry, $12,000 to $15,000 for an acre-sized area. However, we often open that up depending on the client's needs and budget. I don't need to be looking for such small targets, so we might open it up to a 10 by 15 or a 10 by 20. We always try to keep it at in one direction, a 10-foot interval spacing between measurements. So that gives us high resolution along a given profile, and we can open up between profiles and interpolate some of the data in between there. Excellent question.
Thanks, Felicia. Fantastic. All right, moving on here. Another question that was posed is, in the image with the GeoGrid reinforced slope being installed around the pipeline, was the pipeline operational during the slope construction? Bricks, that's probably a question back to you.
I believe that it was, yes. Yep.
And Chris, I would say that's the steeper of the two slopes that was shown there, correct?
Yeah, correct.
Yeah, I actually had application in that particular project, and that line was initially shut in when the landslide was identified. We did open the line up. We applied some strain gauges on that particular line to do some evaluations for a few weeks prior to. Found out that there was no implied strain on the line itself. We recovered and loaded the line and then started in on the landslide repair. So it was in fact live as we did the repair itself. Naturally, that comes with additional implications and safety issues, but we managed around those and mitigated the project accordingly. All right, moving down the line here to some additional questions. Dave, this one's probably for you. What is the difference between Ferc and state guidance on geologic hazards?
It's very similar. Some of the terminology is slightly different, but they essentially, the intent is the same. And that's we had done a full-scale webinar regarding HDDs, geophysics, inadvertent returns, and that was a question that came out of that. And that FERC guidance came out last October, and it's very similar to Pennsylvania's guidance.
Excellent, thank you. Here's another question, Dave. This probably stands with you, and Bricks, you can fill in the gaps. Under what scenario for a building project would a licensed professional be required on site? In addition, would a materials testing and soil technician be satisfactory already on site for compaction testing?
I'll address the first part of that, and I'm primarily Pennsylvania focused at this point. We've seen on pipeline projects with HDD crossings, DEP is requiring a PG to basically sit and observe every HDD crossing. We've also seen on some pipeline projects where with open cuts through wetlands, they want a qualified wetland scientist to classify soils, segregate soils, and direct the backfilling with the appropriate soil sequence. So we've seen that, and I think that the latter part of that question, Bricks, is more towards you and the geotech side of things.
Yeah, so if it's one of our designs and you know, we are kind of responsible for the engineering of it, and we would certainly have one of our soil technicians that has a nuclear density gauge there every day to do that testing. That's not a problem, but we just want to be sure that the contractor is following the steps that are outlined. You know, one thing that commonly comes up is whether to work or not during, you know, after heavy rains, you know, because the material will all, may not be dry enough to do compaction. If we're not there, or if somebody who isn't experienced there, the contractor may move ahead and be placing materials, that may not be adequate, because they have they provided a price to the contractor, and they want to try and meet a schedule, but weather commonly delays things, and if a good inspector is not there, things may not go as planned, if things aren't being watched.
And that ends up costing money in the end when a engineered slide repair fails.
Yeah.
If it's not properly constructed.
Yeah, Dave and Chris, I'll jump in there as well. I know just recently we've had 3 or 4 inquiries kind of post-construction related, where predicated on the reviewing agency. In one of these instances, it was the Federal Energy Regulatory Commission. In others, it was state agencies, where based on the reporting that was done up front and the findings found and recommendations to proceed, the consultant at that time had recommended that licensed geologists or licensed professionals be present during that process. And that's what the permits were initially instituted on or agreed upon on. And in fact, they used general construction inspectors or general site inspectors on the back end. And these regulatory agencies did a site review or did a post-construction review, found out that they didn't abide by the onset of the permit guidelines, at which time they shut them down for no further operation till further notice to proceed. And we actually got involved with coming in and doing some retroactive geophysical evaluations to assure that there was no karst topography or that compaction had been done appropriately. So I would say it's kind of a loaded question to some degree, but making sure that your agreements and your permit stipulations up front are met on the back end as well, and due diligence is made should you get in that post-construction realm of having to prove beyond a reasonable doubt that you did what you had to do. All right, folks, again, I know we're running on 1 o'clock here. Some may have to leave, some may have to drop, but we're going to continue through the Q&A. Again, this is available for 90 days live, that you can come back and review these questions post at that link in the RSVP originally, but we're going to continue on here. Next particular question, does Retwo have internal capabilities to obtain and process up-to-date Lidar for regional landslide delineation and monitoring? I can probably help out here with this, guys. So depending on the magnitude, changes the answer, but locally, for landslides that are found or areas of specific concern, we do have drone particular capabilities that we can fly and get live LiDAR contouring and live ortho photography. If we're talking more of a regional specific evaluation, we do have partnerships with larger helicopter and airplane flight capabilities to fly counties or states or regions, as I said, but we would process all that data in-house, again, through our raster design programs, GIS, and our geophysical group. We've done quite a few of those evaluations. We use specific shading characteristics, then team with the geological background data to conform high, moderate, or low probability areas of influence for potential landslides in the future. And I think we've overlaid that even with mining data in the past and some more of the publicly available aspects as well. All right, another question, and Brix, this one's probably to you on the geotechnical side. Do you recommend any specific deep foundation system over another for karst systems?
Yeah, and it kind of depends on what the project is itself. So if it's a 3 or 4 story or even 12-story office building, my go-to is having micropiles as the standard for that, because we want to seat that deep foundation into rock, and micropiles are a very good way to do that. If it's a lighter weight construction over a karst area, and there are soft soils and variability, there's deep dynamic compaction that can be done. There's also rammed aggregate piers, or geopiers as they're known, which are also relatively economic options for basically densifying the subgrade. But there are some risks to that. That doesn't really you're not getting into the rock, investigating any voids, ensuring that the foundation is into rock. That's why for a heavier building or taller building or tank, maybe something more sturdy like a micropile is the best option. So I hope that kind of answers that.
Thanks, Chris. Felicia, it looks like we got one more here, probably along your lines. As far as what are the accuracies of your geophysical surveys?
Another really good question. So the accuracy of any geophysical survey depends on a couple of things. One, the density with which you collect the data. So the more data we collect, the higher accuracy we have. Again, as I said before, we always try to balance a client's needs for information against the available funds that they have. But in terms of a general rule of thumb for geophysics, we can probably say that if we're giving you an answer, let's say we do a depth to bedrock survey, and we say that rock in a particular location is about 20 feet below the ground surface. With seismic and with most other techniques, the general rule of thumb is we're within about 10 to 15% of actuality. So if we have rock at 20 feet, the reality, the 10 to 15% margin might be 2 to 3 feet within that 20-foot range. So 17 to 23 feet. So it doesn't give you no geophysical technique gives you the crystal clear picture. It gives you the fuzzier picture. An example, again, using seismic that I can help to describe this is if we strip off the soil overburden. So for example, that picture that I gave in the geophysics section showing the bedrock surface at the Antaladi Dam and at Baker Quarry, and you saw that very gnarly bedrock, pinnacled bedrock surface. A seismic survey isn't going to pick up all the nooks and crannies, but it will give you the general sense of what's going on. Picture that surface with a Polar Tech blanket, the soil stripped away, but with a Polar Tech blanket draped over top of that. You're not going to see the individual cutters, but you will see where there are knobs sticking up and where there are low spots and where there are really low spots, things like that. So general rule of thumb for most geophysical surveys is 10 to 15% of what actuality is, and the more data you collect, the higher accuracy in any geophysical survey you will have, but there's a cost trade-off. Hope that answered the question. If not, please give me a call. We can talk specifically.
Excellent. Thank you, Felicia. Well, folks, that does it for all the questions that have been IM'd in and posed via even email. So once again, thank you so much for attending here today. We hope you found it beneficial and informational. You have the contact information. Anything else that would be needed, please feel free to reach out to us, and have a great afternoon. Be safe out there.
Thanks, everybody.